Software, hardware, data, and the communication lines. So which ones of those are the most important to the organisation? Say for SIT, the student grade information and student contact information is an important asset. We shouldn't release it publicly. The financial information of an organisation is an important asset. The software that we run on servers is also another asset. So we have a number of assets we want to protect. And we need to consider which ones are most important, try to allocate a value to those assets. We need to try and consider what are the vulnerabilities, what can go wrong, how could someone get access to those assets when they shouldn't, are not supposed to. What are some threats and what's the chance of attacks taking place? What's the consequence if one student does get the grades of another student? What happens then? Do we lose a lot of money, or does a student get upset, or something else happens? And what's the probability that attacks will take place? So an organisation should consider all these factors to come up with a security strategy. And they often need to consider trade-offs like implementing security mechanisms to implement the strategy versus making it easy for the users to use the system. And many of the security mechanisms will have a cost involved, a direct or an indirect financial cost. So we need to consider, well, what's the cost of implementing those security mechanisms versus the cost of an attack taking place, failing and having to recover. So sometimes, even though we should implement a security mechanism, it may have a very high cost, and it may be a cheaper option not to implement it and just recover if some attack does take place. So that's what the policy to identify those trade-offs. Then the organisation will implement a set of mechanisms to try to complete that policy, and they'll focus on how to prevent, detect, respond and recover to attacks, look at techniques for implementing, and then they need to do assurance. They want to have some confidence that the techniques they've used will work as intended, and they want to do some evaluation to make sure that the techniques are working. It's no good to implement the security mechanisms and then find out that they don't achieve our original policy ideas. We won't cover these details of security policies in this course, but be aware that there are a number of ways to develop a security policy for an organisation, doing risk analysis, identifying the trade-offs, and doing assurance checks to make sure that implementations work correctly. We'll stop this topic. There are some information security principles listed there, but they probably don't make much sense to you until we explain each of them. I will later provide you a document with a definition of each, but I think as we go through the next few topics, we'll come back and some of these principles will be identified, especially things like privileges, least and separation of privilege, open design we'll see when we talk about cryptography, defense in depth. So I'll explain them as we go through the next few topics, not now. They actually come from another document from NIST, which I'll have a link to on the course website. So that finishes our introduction to security. In summary, we want to achieve the objectives normally of confidentiality, keeping our data secret, integrity, making sure it's not modified without permissions, and availability, making sure our computer system is available to the users. And we want to protect different assets and a range of different attacks. So far, we've identified 6 different attacks. Doing something that doesn't modify how the system works. The attacker is passive and they don't need to make changes to the traffic in the network, they don't need to send extra messages, they just sit there and listen. An active attack involves the attacker making some changes to how the system works. For example, they modify a message, they inject a new message. So the difference between those types of attacks, passive and active, is passive, the attacker does not modify how the system works. Active is the attacker does make some changes. The significance of comparing the two is that passive attacks are usually easy for the attacker to perform and hard to detect, whereas active attacks are easy to detect. So the approaches that we use to defeat those attacks, usually passive attacks we need to use techniques in advance to prevent them, whereas active attacks we use techniques to detect them. And we'll see that as we go through some cryptographic techniques. We also said that we can talk about inside or outside attacks, depending on who's doing the attack. We mentioned that there are countermeasures or security mechanisms. They are the techniques that we'll use to implement the security services. So they'll be the techniques to prevent, detect, recover from attacks. And the prevention and detection in particular usually use cryptographic techniques, encryption especially. So the next topic we'll look at those cryptographic techniques. Am I finished? There's 2 more slides. I will not go through these. Most of the lecture topics I'll include 2 or 3 slides at the end, giving some other areas that you may explore if you're interested. You can just explore on your own, like different organisations which are involved in computer security. And in some other slides you may see some future issues or research issues that can be considered. But we can discuss maybe outside the class if you're interested. And you indirectly use it, or you use it on a regular basis when you use a number of network protocols. HTTPS, for example, accessing a secure web server, encrypts your data before it's sent. So in this course, we'll not look at the details of how encryption algorithms work, but instead just say, well, what do we mean by encryption, list some of the different algorithms available, and present some of the trade-offs and types of attacks. Encryption encryption is used for different security techniques. The key one, or I'll avoid saying key, the important one is confidentiality. So let's start with that. How do you keep data secret? Encrypt that data. So our aim is to take our confidential information, our message, and make sure that unauthorized individuals cannot read that message. That's what data confidentiality is. The way that we do that is we take that confidential information, encrypt it, and we use an algorithm, an encryption algorithm, such that anyone can see the encrypted data. We don't care who sees the encrypted data, but the algorithm should be so that only authorized people can decrypt to find the original data. And the authorized people will be identified with the use of keys, secret keys, for example. Encryption is used for data confidentiality of information being sent across a network. We say sometimes in transit, the data is sent across a network, but also for data at rest, data stored on a disk, for example. So the same concepts are used. So I want to encrypt a file that's saved on my hard disk. I encrypt it, and I save the encrypted file on my hard disk. Anyone who accesses my hard disk cannot get the original file unless they have the key. Similar, I want to send data across a network. I encrypt it before I send it. Anyone who intercepts that message, like we did with Wi-Fi, can see the encrypted message but cannot decrypt it unless they have the key. The same approach is used whether it's saved on a disk or sent across a network. Most of the examples we'll use will be sending across a network. So a simple model is that we think there are two users, the two normal users, A and B. A wants to send a message to B, and A and B want this message to be confidential. That means that when A sends a message to B, we don't want anyone else in the world to be able to read that message except B. Of course, A can read the message they created. And for anyone else in the world, we'll represent as just one other user, an attacker, user C in this case. What we'll assume, so user A, their computing device, generates the message, and will send something to user B. We will assume that some other user, user C in this case, who's performing an attack, can intercept anything sent between A and B. Somehow they can intercept. Somehow maybe that they do the attack on a Wi-Fi link, or somehow maybe they simply go to the computer and get a copy of a file, or they tap into a wide link or get access to an intermediate device like a router. But the assumption is somehow the attacker can intercept anything sent between A and B. Therefore, we can't send the original message between A and B because it will not be confidential. So what we do is we encrypt the message before we send it. User A has the original message that they want to send to B. We refer to that message as plaintext. It doesn't have to be text. It could be any format, but the name we give this original message is plaintext. And what we do before we send that is we encrypt it. We apply an algorithm, an encryption algorithm, or a cipher, and it takes as an input the plaintext, and we use a key to encrypt, and the output of that algorithm is what we call the ciphertext. And it's the ciphertext that A sends to B. And the encryption algorithm will be chosen such that there's a corresponding decryption algorithm where when user B receives the ciphertext, they take that as input, they have a key, and they apply the decryption algorithm such that it will produce the original plaintext as output. That's the idea. So a couple of points on that normal process. The encryption and decryption algorithms used at A and B go together. That is, they're related. Sometimes they're even the same algorithm. They must have the property that if we encrypt a plaintext message to get ciphertext, if we decrypt that ciphertext using the correct key, we must get the original plaintext. So the algorithms must return the original plaintext. They cannot return something different, otherwise they don't work. And the algorithms take as an input a key. In this picture, I say that the encryption uses key 1 and decryption uses key 2. They may not be different keys. They may be the same values. So key 1 and key 2 may be the exact same value. In some schemes they are the same. In other schemes they are different. From the attacker's perspective, the attacker can intercept anything that A sends to B, in this case the ciphertext. The attacker wants to find the plaintext. That's their aim. They can easily obtain the ciphertext. If you have the ciphertext, you can try and decrypt that ciphertext. And this assumes that the attacker knows the algorithm used for encryption and decryption, and that will be a common assumption. The attacker knows how he did the encryption and decryption. So assuming the attacker knows the decryption algorithm and they know the ciphertext, what do they need to get the plaintext? What does the attacker need to get the plaintext? They need key, the key 2 in this case. Okay? So the important part here is the key 2 must be kept secret. If the attacker knows key 2 in this scheme, then they can decrypt very easily and get the plaintext. So we'll talk about secret keys. Keys are normally kept secret. In this case, user A and B may know the keys. They cannot tell anyone else, otherwise the scheme fails. It's not secure. And later we'll talk about some different approaches of how to use secret keys. Even if the attacker doesn't know the key, it should be practically impossible for the attacker to either find the key or find the plaintext. And if we have an algorithm for encryption and decryption such that the attacker, given a ciphertext, cannot find the plaintext, then we consider that algorithm strong or secure. And there are such algorithms that we consider secure, so we'll list some of them as we go through. So that's our general model for encryption. Encrypt the plaintext using one key, and the receiver decrypts the ciphertext using a potentially different key. It may be the same. In most of the cases we'll see at the start.